detector effects. Now, if we now want to derive, so I just put that equation out there again, which has been derived many times. Or it has, I don't know whether it has been derived, but it's good to remember. So the amplitude for a new E goes to a new something, doesn't matter what it is, yeah, is in a two-flavor model is given by this frequency. So there's the L over E and the delta M squared. So for a fixed delta M squared, it's just L over E. And the amplitude is given by sine squared 2 theta. Yeah? Now, let's calculate the L over E for our problem here. So the typical L over E is of the order 30,000 kilometers per GeV. That is just because we have used GeV here, because that's the units we have to use, yeah? Which is like the same as if it calculated MeV. So the oscillation period here is just given by setting this guy to pi, okay? We know L, we know E, we know pi. We put these numbers in, and what we get for delta M squared is something like 8 times 10 to the minus 5 EV squared. And there we go. The real value is a little bit lower, but basically what we have done is we've seen a deficit in the spectrum. We have replotted it as L over E. Yeah. We have, now we can derive the amplitude. This is the sine squared term here, by the way, yeah, because the amplitude of the oscillation is given by the sine squared 2 theta, and we have the frequency from this, yeah? The amplitude, as I said, is, so if you go back, is about 0.9, yeah, roughly. If you take 0.9, sine squared 2 theta of 0.9 gives you an angle of 36 degrees, yeah? It's 34 degrees. Okay, so in that simple form, we have just derived this particular mass splitting and corresponding to those through those nuclear neutrinos. So, what we already can see from the data we have at that point, both the solar neutrino data and the data from reactors and atmospheric neutrinos and also accelerators, of course, is there are two different mass splitting, two different frequencies at which these oscillations happen. That isn't so surprising if you have 3 neutrino flavors. And one of them is larger and one of them is smaller. By the way, why can I not do the same simple derivation of the delta M squared with the solar neutrinos taking the distance of the sun to the Earth? Because the oscillations of solar neutrinos do not happen over the whole length from the sun to the Earth. They happen predominantly because of the MSW effect in the sun. Yeah, they are enhanced in the sun. So the majority of the oscillations actually happen at the beginning. Once the neutrinos leave the sun, not much happens anymore. Yeah? So the L, if you want, is not really what you have to do is to do a complete calculation, including the matter effects. Yeah? That's why this simple way of doing it wouldn't work quite in the same way. So we have 3 neutrino masses and 2 splittings. So we have the atmospheric splitting, which is the one, it's called like that because it is consistent with the data from the Super Kamiokande data. Yeah? That is 2.4 times 10 to the minus 3. You derive that from their data. You have the other splitting, which we just derived from Camland, but as I said, we can't do that. quite, but it's the same. If you would do the full analysis, you would see that's the same as what you get from the sun, and that's therefore called the solar mass splitting. So these are the two mass splittings we have. We then can now basically populate, so these are the three mass eigenstates, these bars with the flavor contribution that they have. And the flavor contribution, how much each flavor contributes, is actually just given by this amplitude, the sine square. Yeah? So it looks like electrons only take part in the oscillations given by the solar neutrinos. And this mass splitting here, and this solar mixing angle, which we had calculated before, here is 34 degrees. So if we put that in 34 degrees, so we get sine square 34 degrees is 0.31. So the electron flavor splits approximately 2 to 1 between the two lowest mass states. Yeah? Mm-hmm.
I thought that you had arrived at the 34 by saying sine squared equals 0.9. Was that wrong there?
Sine squared 2 theta. That's the amplitude term, is there?
Okay, thanks.
Okay. Now we have the atmospheric mixing angle, yeah, which we derive to be 45 degrees, and 45 degrees roughly with a large error here. That means sometimes called maximal mixing, because that is the largest value the sine can take. Yeah, so this is why it's called maximal mixing, and this means if we now fill up the rest, that up here, the third state is roughly, because it's maximally mixed, half mu and half tau. Yeah? And here again, basically what we have done here is, because we've predefined from this value, this 0.31, how many of the green stuff comes in here. And because of the 45 degrees, we now just add the mu's on the taus equally to fill up the rest of the eigenstates. Yeah? Okay. The reason the two-flavor approximation works, by the way, here, is because these two splittings, which means also the corresponding frequencies, are basically decoupled. Yeah, they happen at completely different frequencies. So you can pretend it's a very good approximation to assume they are just two-flavor oscillations. Of course, if you do the full analysis, you can't do that and have to take the whole thing into account. Now there's a green slither up there, which could be there or not. But if it is there, it is very, very small. And now we have to see, until a few years ago, we weren't sure how much of the electron flavor actually contributes to nu3 or any of that at all. So what is governing that? So let's just come back to the PMNS matrix just to remind everyone. So these are the different mixing angles which we just defined. And the reason the PMNS matrix is defined like this is just so because you split it up into these different terms due to atmospheric and solar mixing. And we didn't label them properly. But just to remind everyone, the mixing angle, so the theta 1, 2 is the one which mixes the electron flavor with mass states 1 and 2, and that is the solar angle. 2,3 is the atmospheric angle, which defines the mixing between the muon and the tau. 1,3 is the one which takes the electron flavor, and we haven't talked about that yet, into mass state 3. It might be 0, and then there is, of course, this CP violation phase. Now already here you see why this mixing angle theta 1,3 is so important, because up here the term in front of the phase delta is proportional to sine theta 1,3. If that angle would be 0, it wouldn't be possible to access it. So this is why there was a big measurement program to get this particular angle, because if you want to measure delta, if this term gets 0, of course, it's trivially disappears. Yeah. So what is important is to get access to this theta 1,3. Okay, and how would we do that? So this angle theta 1,3 obviously has to do something with the oscillations which are driven by this frequency. Yeah? Okay, the delta M32. So let's look at the oscillation pattern as a function of L over E. The theoretical oscillation pattern has two frequencies. That's exactly what we expect. The longer period here is just our delta M21, which we determined to be 8 times 10 to the minus 5. Okay, this is the Camland measurement which we had at the beginning, or the atmospheric, the solar neutrino value, solar oscillations, which we get for typical L over E's of 30,000 kilometers per GeV. Now, the energies that come out of the reactor are, from antineutrinos, are of the order 3 MeV. So if we now want to look at electron-neutrino survival probability, yeah? So the probability that a neutrino is still an electron-neutrino when we measure it. Yeah? And we want to see these, want to have access to these additional terms, we have to change the L over E to something like 1,000 kilometers per GeV, because of the different frequencies. Before we were at 3,000 kilometers, but we don't, 30,000, we can't change the energy, yeah, because they come out of the reactors. So the only thing which we can change is the baseline. If we do that, we would become sensitive to these points here, yeah? And these points are the points where the this amplitude here is just proportional to theta 1,3, because it is the survival probability of the electrons, which is exactly what we want to measure in these oscillations driven by delta M32. Remember that we had this before. So we want to measure the oscillations driven by this frequency with the amplitude related to still observing a nu E. If we write this as a formula, what it means is that this is the amplitude, this is sine squared theta 1,3, this is the frequency, which is the delta M32 driven frequency. So that's what we have to measure to get access to sine squared theta 1,3. So the first thing we see is a relatively small effect. Because we can't change the energy, we have to go closer to the detector, with the detector to the reactors. And Camland had like an average baseline of 180 kilometers. so to change the baseline, so this is what you would have to do. You would have to go about 1 kilometer. So to get exactly to this dip, you take 3 MeV, you put it in this equation. This point is at 1.6 kilometers, yeah? Now that's not good enough because the problem with a reactor is that we don't know the reactor flux very well. So we have to put another detector right at the reactor to have a relative measurement of the flux close and away. And we do that roughly here at this point, which would be 400 meters. That's already pretty close. I mean, there are other experiments now that go meters toward the reactor, but that's, I'll probably talk about that tomorrow.
Question, does this plot have the solar mixing angle also in it, or is it just
It uses all known, it's just using the best known values, yeah. And of course for illustration purposes, it's, yeah. The problem here is, you could say, why don't we measure these oscillations somewhere here, yeah? But the reason that is a problem, because you have to have, in order to disentangle any of these, you need absolutely excellent energy resolution, yeah? So the way this has been done is by a suite of different detectors. This is one in China. This is Daya Bay, that's close to Hong Kong, where you have a detector, a set of nuclear detectors, which are, so this is the Daya Bay nuclear power plant, and they have arranged various detectors around it at the distances required of a couple of kilometers. Just to show you, this is Daya Bay, it is close to Hong Kong. Hong Kong is a beautiful city, and actually I thought about it because I was in Rio over the weekend. Hong Kong and Rio look very similar. If you take a photograph, they are very similar cities with mountains and sea, and I thought they have a lot in common. The detector I showed before is a scintillator detector. That's what you do, and you put in this, basically you put in the scintillator in here, you put photomultiplier tubes around it. You also have some veto here around it, which you use to contain your vents. The trick you apply here is that you load, and that's quite a common trick, you load your scintillator with gadolinium. Gadolinium is an element which has a very, very high neutron capture cross-section. And so the process I showed you before here actually is much enhanced in this case, because the gadolinium will eat your neutrons and produce 8 MeV gammas, which after about 30 microseconds, and you can then look for a coincidence between the top signal and the bottom signal to really suppress your background. Yeah, that's how you do that. There's another experiment called Reno, that's in Korea. So you see the typical length scales, which I said before, yeah. This is the detectors. They are nicely aligned, which is of course nice because it's easier, the geometry, yeah? And then there's the far detector and the near detector. The far detector are on opposite side of the reactors, but who cares, yeah? Because of course the flux goes in every direction. It's not like you have to measure the same neutrinos, you can do that in any direction you want. As long as everything is symmetric in the detector, yeah? And in the reactors. This is not the latest measurements, but the first set of measurements here. So this is now, what do we see here? We see the energy distribution. They measure, this is Daya Bay, Reno, and then there's another experiment in France. That's double show. And in order to get rid of the rate problem, they just plot the ratio of the far over the near detector, yeah? And when you do that, you see clearly a dip in all of these detectors at this energy around 3 MeV, which is consistent with sine squared theta 1,3 of about 0.1. All of these got more or less the same result. This is a very, very large value, actually. It could have been 0. It's not a very large value, but it could have been 0. If it had been 0, all experiments like Dune or Hyper-K would have been screwed. It wouldn't have been possible to access delta in the same form because this angle is in front of the phase, okay? Now, just to show you as an aside why it is so important to measure the far over near detector ratio, this is observed by all 3 experiments. This is the data compared to the Monte Carlo, an absolute prediction for the rate from the detector. And if you look at the ratio of the Monte Carlo, you see there's a peak at 5 MeV. Every one of these experiments sees it. The explanation for this is most likely, well, not likely, it is nothing to do with neutrinos at all. It is something not understood with the uranium in those reactors. There are some nuclear processes which generate this 5 MeV peak. And there are theories which describe, models which can describe that and so. But if you had just looked at this without your near detector, not as a ratio, you would have thought there's an effect there. So it just shows how important it is to make these relative measurements of ratios and not absolute measurements. Yeah?
What would be the accidental contribution that box, like fast neutral, accidental?
Accidental, well, I assume that, so they look for coincidence between the gadolinium and the other photons, and some of them will be just random coincidences, yeah? So I showed this in my talk on Wednesday, or when it was, and this is now the oscillation formula written not in 2 flavors but properly, but you see the most important things. So this is how you do, so we have all the rest of the matrix together now, yeah? Now we want to get delta as the last missing piece. Actually, the other angle which isn't so I told you that theta 2,3 is maximal. That's actually not so clear. It has a large error, and it could be, is it really maximal? Does it belong to the left or the right side of 45 degrees is another question. But the most fundamental question is what is delta Cp? And also what is the mass ordering? So looking at that equation, I'll spend a little more time than last week. So first, all of these proportional to sine squared theta 2,3. Yeah? So cosine. So this, but this value is relatively large, so we aren't too worried about it. The delta term is proportional to sine squared theta 1,3. So if that had been 0, there we go. Then here are these terms with an A in there and the length, and that is the Fermi constant times the number of electrons divided by square root of 2. So these are matter effects, because the matter effects will be proportional to the electron density in your beamline, yeah? The oscillation frequencies are then given by these deltas, just to make it a little shorter for the various things. So what you can do now, if you build a long baseline experiment and you have a broadband beam as we have here, you just put this, you plot this equation, takes an afternoon, and you put it over that, and it will modify, depending on the parameters you choose, your energy spectrum. Yeah? And that's what you actually measure. So you compare your near detector, your flux, with your far detector. This would be your original neutrino flux, and as we learned this morning, it's tricky to determine that. And then you look at this modification and you fit that. If you're going to higher energies, this is the second oscillation maximum, so you can actually see more than one oscillation maximum. Yeah? Of course, this fit is what you have to do is the more you can fit, like if you can fit the whole energy distribution, the more information you can extract. It depends both on the amplitude of these effects, but also that you can fit if you can fit the whole energy spectrum, you can really derive as much information as possible. Operating long baseline experiments, which don't have the primary goal to measure delta perhaps, but actually started originally, T2k is here, one of them, started to measure theta 1,3, are T2k and NOVA, and this name is just there because I stole it from another talk I gave. I forgot to remove that. So they are fundamentally different. So the NOVA experiment is an experiment at Fermilab, and it points a beam to a facility in Minnesota up here, and has a path length of about 800 kilometers. Yeah. The detector is a scintillator detector, and the near detector and the far detector are completely identical, just not in size, but the technology is completely identical, which helps you to get rid of systematic effects. The T2k experiment is completely different in that sense. It has a 295-kilometer baseline, again going across Japan. The near detector is a classical spectrometer with calorimeters and stuff like that, magnetized. The far detector is just super K. It's the big water Cherenkov thing. So completely different technology. That's challenging because in one hand you can optimize your near detector to do the measurements you want, but on the other hand you don't have cancellation of your errors. This is how NOVA events look like. It was 1/4 yeah? Yeah, okay. This is how NOVA events look like. So NOVA has a 14 kiloton far detector and equivalent near detector, and it's liquid scintillator, it's oil. This is basically just as a very simple detector in a way from the structure how it's built. It's like tubes with this oil. Yeah, it's read out by APDs, which are avalanche photodiodes. This is like a next generation, readout detector. The way you reconstruct these events, you just have hits in these scintillators, which you reconstruct. And this is a typical event display, how they look like. So this is the beam direction. And here, for example, you see a muon and a hadronic recoil. Very nice. Actually, I won't talk about this in more detail, but NOVA has actually done a very good job in analyzing this data using modern analysis techniques like convolutional neural networks, which I mentioned before. As I said, the T2k detector in Japan is different, and so this is the rings they see, and we have seen those rings before, electron and muon. But then the near detector is a completely different beast with an ecal, and you want to reconstruct pi zeros and different other things. And this is a completely different philosophy. So what do these experiments see? So they always measure two things. Remember, we start from a muon neutrino beam, and we want to see electron-neutrino appearance. So when we look at muon neutrinos in the far side, we often call that disappearance, and when we see nu e, we see appearance. Of course, in both cases, it's a positive signal, yeah? It's just how the language is chosen. We expect more nu mu's than nu e's, and on the top we see now if you want to do CP violation, you want to do nu mu's and anti-nu mu's, yeah? And this is the signal, and again, this curve here would be the unoscillating, in case you still don't believe in oscillations. they're definitely oscillating, yeah? There is a difference of about, if you can see that, of about a factor 3 between these signals, and that is just for the reason I discussed in the morning, because the nu mu cross section and the anti-nu mu cross section are different by a factor of 3, which isn't that great, but you know, that's just what you have to live with, yeah? The nu E appearance data, which in a way is an even stronger indication of oscillations, is shown here. So they plot this in 2 dimensions with an angle and energy. I didn't find nicer plots, but you see the individual events are very well described. The events are the black dots with their expectation. Nova does the same thing. This is their disappearance data. You shouldn't take at face value that these antineutrino events are lower than this, because the number of protons on targets are not given here, so they might not correspond. But it's not surprising that the antineutri is lower. And they also see nu E appearance. And the way they plot this, they have 2 different samples. So this is like 2 plots next to each other, but you see there's a few events appearing. It's a very small number, yeah? Nu E appearance is a small effect, yeah? That's after years of data taking. Okay, you fit all that, and you can extract the oscillation parameters. I won't list all of them, what they do, but let's just look at delta CP. So, and the mass ordering. So again, on the left, we always have some type of significance. Sometimes it's called minus delta log likelihood. Sometimes it's called delta chi-squared. These are related. Actually, you can show relatively easily that the 2 times the log. So often when you have a log likelihood, there's this factor 2, and the only reason for that factor 2 is that if you write the 2 there, it is almost like a chi-square. Yeah? So chi-square and minus 2 log is basically the same. The best is in the minimum when you do the fit, because we don't know which ordering is right, normal or inverted. So the fit is done both under the assumption of the normal mass hierarchy and the inverted hierarchy. And the delta CP parameter is not known, so it's down there. And just to confuse people a little bit, this is nova, and this is nova, this is T2k. 0 is here and 0 is here, yeah? So the axis is shifted, because an angle can always be from minus pi to pi, or from 0 to 2 pi. Now you see that both experiments have a little bit of sensitivity to delta CP. It's not great, though. All of this is of the order, you know, this is all perhaps 2 sigma maximum. So one should take that with a grain of salt. But if you see the difference between the normal and the inverted curve, the normal and the inverted curve, you see that both experiments very strongly favor, but kind of favor the normal hierarchy over the inverted hierarchy. The T2k people also say they see, you know, because in statistics you have to be careful. They can't claim a measurement, so they say CP conservation hypothesis is outside 2 sigma interval. That's kind of a bit of a wishy-washy statement that they see some indication, but it's interesting, but you know, it's not statistically very strong. Why is this actually such a strong indication? Why is the delta especially? So this is they are more sensitive. So this is a problem with experiments in general in statistics. Whenever you do an experiment, you should look at your expected sensitivity before you do your experiment. Your expected sensitivity is the one you would get if you have an unbiased experiment and you repeat it in a frequentist way hundreds of times, yeah? And you see, on average, or the median, you usually use the median, you get a particular sensitivity. Your real experiment will give you one value and not hundreds. You might get lucky or unlucky, and your result is better or worse than your sensitivity. People always get nervous when your result is much better than your sensitivity, because you feel like, is it really true that they got so lucky? Yeah? The T2k result is more sensitive than maybe expected, and that's largely due to the fact. So here, this is the number of observed events, and this is just a little bit of confusing stuff. FHC, forward horn current and reverse horn current, that just means nu E and anti-nu E. That depends how the horn, which we talked about this morning, is working. And then they have different topologies for muon and electron type events, and they have them here. Now if you see what they observe, and then they give you the expectation for different delta CPs. So for example, here, delta CP of 0, they would expect 61 in this channel and 6 in this channel. They observe 15 and 75. If you have a delta CP of minus pi half, which would be a large value, they would expect 74 and about 7 events. That pulls the fit in that direction. Yeah? So what's the global picture? What do we know? There are some things, so there are people like NewFit which are putting all the data in a big machinery and then fit everything. You have to assume that there's only 3 active neutrinos, and then you can get values for theta 1, 2, delta m squared 2, 1, delta m squared 3, 2, sine squared 2, 3, sin squared theta 1, 3, and delta CP. You see, some of these are, this is funny because it's actually the one which we haven't been knowing for such a long time. It already has a very small error. That's the one which I talked about, the 0.1, yeah? 1, 3. And all of these curves are shown for normal and inverted hierarchy assumption. And you see it doesn't look good for the, so sometimes it's called O, normal ordering and inverted ordering is the same thing. I mean, people can discuss for hours whether it's the same thing or not, but it's the same thing. So this is the normal hierarchy, the inverted hierarchy. And you see the assumption that the inverted hierarchy is true always gives you much worse delta chi squared. So this is, of course, not uncorrelated. You always use the same data, so you shouldn't add this up. But at every given point, it's hard to ignore. With delta CP, I think the judgment is, the sensitivity is still not there to make a strong statement. And yeah, and this is the angle theta to 3, which we said was a maximal, which means that sine squared, so 45 degrees is this, so it's 0.5. There seems to be a tendency, I think that's mainly coming from NOVA, that it's actually more on the right side of this. By the way, why measure all these angles? Because I think it was mentioned last week when Andre was giving it, because one of the things we know, the CKM matrix and the PMNS matrix look very different, and there could be symmetries. One possibility is that the if the structure of the PMNS matrix would be very simple, and you would have certain terms, like 1 over square root of 2 or 1 over square root of 3, for example, yeah, then there could be an underlying symmetry which explains it, which we don't know yet, but that's what theorists or model builders do. They try to then explain the particular structure of the matrix in terms of models. Okay, so why delta CP is important we talked about last week, because of leptogenesis and all these things. How can T2k and NOVA do in the next years? Well, statistics is always a problem once, it goes usually with square root, because that's how statistical errors go. So they can actually, so this is their significance for mass hierarchy in, this is green, for CP violation is this. So it will go up, but the sensitivity. So this is not the real data. This is what I said before. You expected sensitivity. It goes about to 2 sigma, which isn't bad. The normal standard for evidence, as we say in particle physics, is 3 sigma. For discovery is 5. Now, some people say for the mass hierarchy you don't need 5 sigma because you only distinguish two hypotheses. Yeah, you could do that probably with less statistical significance. And similarly, there's NOVA, and overall, I would say by the time the next generation experiments turn on, we expect 2 to 3 sigma on CP violation. So this is the next generations, and that is what I will end with in the next 5-10 minutes. I've shown that before, but I just wanted to put it here again because it's just nice. As I said, there are 2 fundamental length scales. This is the width of the island in Japan. This is the width of the United States. And if you build an experiment at 200 kilometers and you want to optimize this term, you have to use energies below 1 GeV. And if you go to larger distances, you optimize, you have to go to higher energies. Yeah? That defines both your beam, but also your detector, because Water-Cherenkov has a low threshold for electron and muons, but it is not very good at energy reconstruction. You don't need that here because you need that here if you want to reconstruct that spectrum which we had before. So that's why liquid argon is a good choice of detector here. It helps you to reconstruct this energy. Yeah. This is hypercam-Yokande. So this is basically the near detector will stay the same. That's the plan. It's not clear whether it will be built, but the near detector would be an upgraded version of the current near detector of T2k. But you would build a new Water-Cherenkov detector in a new cavern a few kilometers or whatever away from Super K, which is called Hyper K, and it's much bigger. And the current plan is to have it like 186 kilotons. This is much more than the 40 kilotons of Dune because water is just cheap. Yeah, simple. The other thing you always want to do is increase beam power, as I've said with you. There's a variant on this plan, and I was just in Korea 2 weeks ago. Many people are excited about this. So if you look here at the beam, this is from this Japanese facility, J-Park, where the beam is produced. This is Hyper K, and you then put, you calculate the beam at different angles as we did with the equation I gave in the first lecture. You notice that it ends up in Korea, on the other side of the Sea of Japan. And so you could put, if you want to go to a different baseline, and people talk about that, a big similar Water-Cherenkov detector into somewhere in Korea. They have a lot of mountains there. It's a very mountainous country. This is just dreams right now. People talk about it, but there's no money for that. I've talked about Dune. I'll not repeat all of that. Dune is the other option. You go from Fermilab to South Dakota and do that. So what's the sensitivity of those 2 experiments in terms of CP violation, Hyper K and Dune? So as I mentioned before, it goes to 0 at 0 and pi for trivial reasons, because you can't discover with a certain. So here we put the 3 and 5 sigma. This is the delta chi-square between no CP violation, which means 0, and what we observe. And of course, trivially at 0, you can't do that because if it is 0, that definition doesn't even make sense anymore. Yeah, because it's the delta chi-squared is the difference in the statistical significance between whatever you measure and 0. And if you are at 0, it's pointless. Yeah, and that's why. And same with pi, it looks like that. But in the regions where, like delta CP is not 0, in most of them, you get 3 to 5 sigma after a few years. very similar also in terms of the precision. And that actually shows you this with a 0 again. This is this resolution as a function of years. As I said, it's about 10 degrees, about what you get in quarks. And here now, you might not discover it when it's 0, but you can measure it very precisely. Yeah, that's a bit weird, but it makes sense if you think about it. If the value is 0, you can still determine the range with very high precision. Yeah, so of the order 10 degrees. Same here for hyper K. Before I end, something I've also been involved in for a while, but not that much anymore, is Icecube and also KM3net. So another way to get a huge neutrino detector going is what we have done so far. We have dug a hole and filled a detector with some material. Well, let nature give you the detector, okay? And one way of doing that is to go to the South Pole and take a big slab of ice, yeah? I think some of you have never seen snow. Is that right? If you've never been in the winter in somewhere where it's snow, then this must be a weird place to go. I mean, I have a picture here. So this is the South Pole. They actually look for people to. So there's summer. Okay, there's this whole summer-winter thing. I'm a complete Northern Hemisphere person, just to explain that. And the fact, this is actually the first time in my life that I'm in the Southern Hemisphere. The fact that it is winter here is so weird. Because the reason it is so weird, because it's not the temperature, I'm okay with that, but the sunset is so early. The whole astronomy is wrong on this side. In England, where I live, the sunset this time of the year is 11 p.m. and the sunrise is at 3:30 a.m. Okay? That's summer. Sitting in the garden and it doesn't get dark. Okay? And here it's 5 p.m. and it's getting dark. It completely gets me. I mean, I have to say, that's really confusing. Anyway, on the South Pole it's even worse because it's 6 months of darkness and 6 months of thing. And the normal people working there go there for the summer, but they are winter overs. You get there, to work on the day. They don't get you out because they can't fly. You know, if you are there for the winter, you are there for 5 months because they are not allowed. They cannot fly during the Antarctic winter because it's too cold. Well, anyway, the thing with the ice is it's very, very clear. Because so different from what you expect, yeah. So you can use it for light. There are some. So just to give you the scale of Icecube. Now I lost the. This is the Eiffel Tower. That doesn't tell you very much. This is 324 meters, probably the highest high-rise in Sao Paulo or something like that. Yeah. So this is it's 2.5 kilometers. It is deep down. Okay. This ice is very clear. There's some dusty regions, but you can correct for that. Yeah. Why does it have to be clear so that light doesn't get rescattered? What they do is now there's a very similar type of detector, and that's here shown in the back. It's KM3net, and there's Antares, and this is there. You don't go to ice; you go to water. Water has some advantages, some disadvantages. The scattering is less. It's easier, of course. And KM3net or Antares will be in the Mediterranean, which is a much better place to spend your time than the South Pole. You can deploy your detector more easily, obviously. Yeah? You just do it from a ship. But, so these are, but otherwise similar technologies. What you do is what is actually the detector? So the Super K is a lot of water and PMTs around it. Here you don't do that. You couldn't possibly do it. So you put strings of so-called digital optical modules. These are spheres about this size, glass spheres or plastic transparent. Inside are photomultipliers and the electronics. And you put them on cables and you string them down. So every few meters you have one of those and you just drill down and let them go down. And the way you reconstruct a signal now is a new mu, or so it creates a muon. A charged particle will emit the light, and the light you detect in these optical modules, and you'll see some kind of pattern, and from that you reconstruct how it looks like. Yeah, it's not very straightforward, to be honest. So they have like I forgot how many strings. I think 89 is Icecube. And then there are, now the problem is, this is a cubic kilometer of ice. Now, Icecube is really focused on doing high energy neutrinos, and for that, it's okay if your DOMs are far apart. If you want to do oscillation physics, you want lower energy neutrinos, the one come from atmospheric neutrinos, and the only way to see those is you have to make your detector denser. Now you can't do that, that's too expensive, but you can do it in some sub-areas. And that's been done in something called deep core, and there are plans to do something also called Pingu and Orca for KM3net, to have subparts of that detector which is denser instrumented. Okay, so the way you do your measurement now is you use, as an analyzer, the Earth. You have, similar to what Super K has done, you have the nu mu and coming here, and the neutrinos they observe, the ones we are interested in, are the ones that actually go through the Earth, yeah? And you exploit two effects. One is that there's a different oscillation probability for news and anti-news, and there's a difference between the flux and the cross-sections for neutrinos and antineutrinos in atmospheric neutrinos, yeah? As we've seen before. I've mentioned this before. The difference between news and anti-news because of the charge asymmetry of the cosmic rays, yeah? And then you basically get a pattern which depends on the mass hierarchy due to these differences. The oscillation pattern of these where it goes through you have to know roughly how the core and mantle and so the Earth looks like, will change the oscillation pattern. This is how these events look like what we'd call a charge current, or this would be like a muon track. This is a hadronic final cascade, yeah. So and you see a lot of this is an event display where the size of the color is the time, the size of the ball is how much energy was disposed. You see how the signal goes from here to here, and then you reconstruct how your muon went through, because these are the strings, yeah? And on these strings you get a different amount of light, yeah? There is an application for neutrino physics. A minute? Is a minute okay? Yeah. I was asked for an application for neutrino physics by Mexican television a few weeks ago. And the only thing I could come up with, you're under time pressure, was you can actually use something like that to beat the stock market or bet on a football game, yeah? When a goal is, you would be faster than because the neutrinos go through the Earth. If you could reconstruct the bits, you can beat the transmission of photons around the Earth. Think about that. Okay. So the way you do the mass hierarchy is by just plotting the difference between the expected rate in energy and cosine, so where they come from and the energy. And this is just the difference between these type of events I've seen track like in Cascade, which you would see just the rate assuming inverted or normal hierarchy, and you see clear differences. And these experiments can actually also determine the mass hierarchy, which is terribly important also for the type experiments which we'll see tomorrow, like neutrinos double beta decay, has tremendous impact. Sorry for being a bit slower.
Okay, let's get a couple of questions. Stefan, is it possible that reactors from around the world could impact on Kamsland measurements?
Other reactors?
Yeah, from like
1 over
everywhere.
R squared.
What? Sorry?
1 over R squared saves you. The flux goes like 1 over R squared. So then, you know, other reactors won't, you know, they're just too far away. Yeah.
One more question.
Anyway, to avoid that noise, do they take data with the reactor off?
Sorry, can you say that again?
To avoid that noise, do they take data with the reactor off?
Oh yeah, yeah, absolutely they do. They take data with the reactor off. Now, of course, you know how it is in the priority of people. If those physicists go to the reactor people and say, by the way, can you turn off your reactor for a week? They have to do some systematic measurements so I can do my master's thesis. It's not going to fly. But they have to do that anyway for maintenance. And so they'll use that time to do that, yeah.
Okay, let's thank again the speaker. And if you have questions, there is a coffee break so you can ask. But before that, we go to the experiments.
Okay. Well, sorry for not giving, as promised, the information before. For tomorrow, you will have your personal schedule, but in fact, it was much difficult as I thought. I have to break the promise that everybody will do the first. So, because some experiments were busy, so at least 3 of the first 5 experiments, everybody will do it. So I hope you will not be angry with me. So what I will do, I will explain where it is experiment. I will give the name of the person that will go to this experiment today, okay? And after the coffee break, when Martin hands the bell, you go directly to your experiment, okay? So experiment number 1, that is the gamma ray experiment, is in the first floor. So be aware that when you arrive to the first floor from the stairs, you have a hall that have big tables. We have 2 experiments there, and the rest of the experiment are after cross this big hall. So you go, you cross the 2 experiments that are in this hall with the big tables. We will be there just to help. And then you turn to the right, and all the other experiments that are in the first floor are in rooms over there with a sign in the door. So you will not get lost, but you need to go through all the corridor, this hall, okay? So experiment 1 is in first floor, in room 108, okay? And have the sign in the door, and the persons are William de Carvalho Vieira, Javier Israel Reynoso Córdoba, Tesio Rogerio, blah, 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 y Mariano Esteves Chavez. I will say 2 names, is enough, okay? Ah, that's nice. The 4th I mentioned are here. 1. Oh, so that's so bad. Again, William, Javier, Tesio, and Mariano Esteves, okay. The second experiment, that is the TPC, is in the hall, in the first floor, at the back, and we have 9 persons. So Brenda, Felipe Loan, that is not here, Lucas Oliveira, Beatriz, Ana Fogel, Rafaela Ramos, Courtney, Enrique Vieira, y Marcio de Souza. Okay, you go there. You will have 3 groups. Experiment 3 is in first floor in the corridor in room 109, so in front of the experiment 1. And we have 6 people: Diana, Breno, Victor Branco, Felix, Rafaela Rodriguez Rossi, and Victor Golo. Then we have the experiment 4. Experiment 4 is in the 3rd floor. We have some teaching rooms, and it's in this room number 3 in the 1st floor. And we have Luis Ricardo, Carolina Queiroz, and Marco Vinicius. Okay. Then we have the experiment 5 is in the same room that experiment 4. Okay, so it's room number 3 in the 3rd floor. We have Victor Prestes, Ariel Zuniga, and Glauber Rafael. Okay. Then we have experiment number 6. Experiment number 6 is in the 1st floor. It's Arapuca experiment. It's in the room 102. So we have Jairo, Lucas, y Felipe Garcia. Okay. Experiment number 7 is in the 3rd floor, is in the room number 1, and we have 6 people: Ali Wen, Carlos Gustavo, Perla, Rafaela Wilchis, or something like that. How it is? Okay, very difficult for me. Sobrinho, this is much easier. Bruno Passarelli, and Victor Barreto de Melo. And then you have experiment number 8, that is in the 1st floor in room 105. You have Yusef, Iago, and Jessica. Okay. Then we have experiment number 9 that is in the hall, in the 1st floor. The hall is the first experiment when you open the door. That is a muon decay experiment. Gabriel Damián Zapata, Eric. Você não é Gabriel? Ah, okay. Damián Zapata, who is? Okay. Eric. Okay. Clara. And then we have the last experiment, that is experiment number 10, that is in the computer room. If you have your own computer, you have to bring there. It's in the 3rd floor. It's in front of the teaching rooms. Some of us will be there because it's not clear where to come in. That will do the Fermi lattice analysis, and it's Leticia Cavalcanti, Manuel Schreck, or something like that, Mariano Ruben, David Bastos, Ana Botti, Giovanni de Souza, Gabriel Sampaio, and Andresa Rodriguez. So, is someone missing? That's good, otherwise we have to stay with me, that is not good. So now we have the coffee break, 15 minutes or something like that, and we will start very sharp when Martin makes the song. Everybody goes to his place. Edivaldo, Martin, me will be around trying to help you, okay? And tomorrow, as every day, very sharp, 10 minutes before the first lecture.
And just a reminder that tomorrow is the barbecue, so be prepared to go from here directly to the barbecue place. Probably you've got an email. If you didn't, we will send you the information. But it's 7:30, so be prepared to go from here to the barbecue. So. Okay, it's after the experiments.